Number 5, why must the Kelvin temperature scale be used for gas law problems? Okay, well, let's draw two thermometers here. And let's say this one is the Celsius scale, and this one is the Kelvin temperature scale. Now remember, boiling water in Celsius is 100 degrees. That was determined by Anders Celsius based on his mercury. And in Kelvin, it's going to be 373 Kelvin. Another trick here, remember that with Kelvin, there is no degree sign. You just say 373 Kelvin. Okay, well then 0 degrees Celsius is 273 Kelvin. And what this means is that negative 273 degrees Celsius is going to be 0 Kelvin. And 0 Kelvin is an important value because it is the temperature at which all particles stop motion. Remember, there cannot be a temperature colder than 0 Kelvin because there's no way molecules can move slower than to stop moving completely. Think back and realize that temperature is based on the speed of the molecules. So a temperature of 373 Kelvin, the molecules will be moving relatively fast. At a temperature of 273, the molecules will still be moving but slow. And at 0 Kelvin, the molecules will not be moving at all. And so this is the reason why Kelvin is used for gas law problems, because the temperature scale here cannot be negative value. And so this scale is more appropriate for gas law problems because 0 is the point at which motion starts, because it is stopped moving completely. And so as we increase here, the molecules move faster and faster. If we were to use Celsius, then negative 273 degrees Celsius would be the temperature at which molecules stop. And so we would have negative values here, which would cause issues when we compare with pressures and volumes. If you think about pressure, pressure is the particles bumping against the wall, and there's no way that you can have negativeness of particles bumping against the wall. Just like you can't have a negative volume. And so a zero liters means no volume. 0 atmospheres means no pressure, and so therefore we use 0 Kelvin to mean no movement of molecules, which is where they're stopped moving. That makes much more sense than using negative 273 Celsius as the temperature which molecules stop moving. So the key reason why is because 0 is the base of the temperature scale at which particles stop moving. Number 6, convert the following temperatures to Kelvin. Remember, to go from Kelvin to Celsius, or from Celsius to Kelvin, we add 273. So to each of these numbers, we just add 273. 50 plus 273 would be 323. 323 Kelvin. 25 plus 273 would be 298 Kelvin. 0 plus 273 would be 273 Kelvin. Now sometimes students get confused with these negative values here. Negative 35 plus 273. Even though it's negative, you still add 273 to it. And so if you take negative 35 plus 273, you get 238 Kelvin. And then of course negative 273 plus 273 would be 0 Kelvin. So key point when you are converting, just add 273 to your temperatures there in Celsius. All right, this is now station 2 of Team Ziggurat. It says for particles, temperature represents the, and as we've discussed with our thermometers and our scales, temperature is going to represent the speed of the particles. So a cold temperature means the particles are moving slow. A hot temperature means they're moving fast. Number 2, for particles, pressure represents, now pressure is going to represent the bumps against the wall of the container. So here we've got a box, let's say, of some gas particles. As this particle bumps against the wall, that is going to cause an outward force on this container, and so that is what the pressure is going to be represented as. So a high pressure means that the particles are going to bump against the wall more. A low pressure means the particles will bump against the wall less. Number 3, for particles, volume represents the space of the container. So a low volume container might look like this. A high volume container might look like this. Okay, that's volume. Number 4, when temperature increases, pressure blank. This is a blank relationship. Explain why. Okay, well, if temperature, so think through this problem, I'm thinking, if temperature increases, that means the speed is increasing. And so if the speed is increasing, then therefore the particles are going to hit the wall more often. So therefore the pressure is also going to increase. Let's draw it out. Let's say we've got this box of gas particles here and got some particles in here. If these particles go from slow to fast, then they're going to bump the wall more, and so therefore pressure increases. Explain why. So the best explanation would be that as particles increase speed, they bump into the wall more. And of course this is a direct relationship, because as temperature goes up, pressure goes up, so those are directly related. Number 5, when temperature increases, volume blank. This is a blank relationship. Why? Well, I think the best example for this is the balloon. When we put the balloon in a freezer, the size of the balloon, or the volume of the balloon, decreased. And that's because the particles are moving slower. So of course, if the temperature increases, the particles will be moving faster, so volume will also increase. And that is going to be a direct relationship, because as temperature goes up, volume goes up. And the best reason why would be that as the particles are moving faster, they will bump into the wall more, which is going to cause the size of the container to expand. Now, a tricky one with this, if you have a steel box here made of metal or steel, then of course the volume of this box is not going to expand, so the pressure would go up, because as the temperature goes up, the particles would bump into the wall more. But if you have a flexible container like a balloon, then as the particles increase speed, they're going to bump against the wall more here, which will cause the balloon to expand and the volume will go up.